It is the second part of section 7.2, properties of the singular value decomposition. In the first part, we introduced the SVD and considered its algebraic and geometric interpretations. Here, we'll discuss some properties of the SVD. Let's see the theorem. A is a metric in n by n dimensions, and U sigma V transpose is the SVD of A with singular values from sigma 1 to sigma r are positive, from sigma r plus 1 to sigma n, this value is 0. Then we say rank of A is R. And also here, the corresponding component, VR plus 1 to Vn, are a basis of null space of A. Now, range of A must be here span of U1 to UR. We already know that A of Vj is same as sigma j uj. So here, and there must be here now range. The collection of uj must be the range. And also here A for dyadic decomposition. And originally, this value must be n, but from sigma r plus 1, these are 0, so that you can put here r. If you try to measure a L2 norm, metric norm, then there must be sigma 1. And if you measure Frobenius norm, and norm squared must be the sum of the singular value squared. So in exercises 2 and 3, the problem is given, and also hints are given, so try to prove it yourself. Okay, if we try to get, if it is, this position is a maximum, that is a 2 norm, but rather than maximum, okay, original definition of a 2 norm is here, that maximum. But now, if you try to measure minimum of this quotient, then now that is the smallest, the singular value. And A is a square metric, M is n, and if inverse of A exists, then here condition number of A can be defined in this way. A 2 norm times A inverse 2 norm. A 2 norm is sigma 1. Now A inverse 2 norm is 1 over sigma n. So that is sigma 1 over sigma n. Okay, this condition number plays a very important role in dealing with algebraic system or some metric algebra. The smaller, the better. Okay. Now A is the metric as usual, and we assume rank is n, which means full rank, and with singular values from sigma to sigma n, every values are positive. Then here A transpose A inverse norm, okay, and A transpose A inverse A transpose 2 norm, and this can be here computed like this one. For example, now in a sense, A transpose A 2 norm that itself is now here, and that is once okay, if you try to get, for example, A transpose A 2 norm, then that is the same as a sigma 1 squared. But now, once you are taking inverse, then, okay, there, in a sense, eigenvalues are from 1 over sigma 1 squared 1 over sigma 2 squared, and so on. So the last one is 1 over sigma n squared. So now this is the largest one, so that you have this value. In this way, you may roughly prove these norms. Okay. Now here, A transpose A inverse, and A transpose is called the pseudo inverse of A, while this is called the pseudo inverse of A transpose. And if A is now U sigma V transpose, the singular value decomposition, then the pseudo inverse can be organized in this way. And then now, usually we are using notation A plus. And okay, now how is it useful? And here, for example, if you are considering least squares formulation, so that, okay, now minimum of ax minus b norm squared, then by using that one can be considered in this way. We are trying to solve the problem ax equal b, and with a minimum error, and by using normal equation technique you can solve that. So the A transpose A, and now here x is the same as A transpose B. So that once it is invertible, then you can say here now x is A transpose A. Okay, that must be transpose, right? And inverse and A transpose B. So that is exactly here this one. So it is called the pseudo inverse of A because we start with this one, but A is not square metric, and it is a tall metric. Yes, A is in general here all m by n, so that once m is not n, then and there's no inverse. However, if you consider this one, then here it looks like inverse of that one, because now x is obtained through this algebraic manipulation. So we call it pseudo inverse of A. Now, if A is given in this way from singular value decomposition, then exactly we put here transpose and A and its inverse and A transpose, and then you can reach at that one. So it looks like this one. Okay, so start with AX equal B. Then A is replaced by U sigma V transpose X equal B. Then from this one, here first we are applying inverse of U, which is U transpose, then sigma V transpose X equal U transpose B. And again, we are applying sigma inverse of sigma, then now V transpose X is the same as now inverse of sigma and U transpose B. And one more time, we apply here inverse of V transpose, which is V, and so that X is the same as now V sigma inverse and U transpose and B. So that is now the pseudo inverse. So when you solve this problem, just replace A with its singular value decomposition, and then now step by step you apply inverse, then you can reach at here this final equation, and this portion is the pseudo inverse of A. Okay, here now A is the usual metric with rank R, and U sigma V transpose is the singular value decomposition with from sigma 1 to sigma r positive. Okay. Then for k from 1 to r minus 1, we can write in this way. It's approximation, and this is written rather than r, we are choosing k, so it'll be an approximation of a. Now here ak, rank of ak must be k, and a minus ak must be here sigma k plus 1. Quite easily you can prove that. And also Frobenius norm, here you can prove that one. In fact, there's norm squared. Okay. Now, but the more important thing is this portion here. And this norm is same as for every possible norm. Among them is smallest. Here now, the rank of B is now less than or equal to K. That means that AK is closest to A. Okay, now A has a rank R. Now AK has rank K, but among every rank K matrices, AK is the closest metric to A. Okay, that's the meaning of this theory. Okay, here the AK can be written in this metric form rather than dyadic decomposition. You can write in this way. So sigma K is just the diagonal of from sigma 1 to sigma K. For remainder, the singular values is 0. Okay, AK. So now for that one, you can consider pseudo inverse of AK. Then that is now AK plus. And here, that is analog of that one. Now V sigma inverse and U transpose. Okay, here V now sigma K plus and U transpose. Because now sigma K has only non-zero over there up to K and every else 0. So it has no inverse. However, now we may consider, in a sense, a pseudo inverse of sigma K. So only for these non-zero, the singular values, we are taking their reciprocals, and for zeros, we keep the same. And that is now sigma K plus. By using that metric, we can define the pseudo inverse of AK. Okay? So that when you try to solve, for example, the least squares problem, and we start with again AXB, and rather than, okay, even though it's full rank, A is full rank, so that normalization technique is working. However, sometimes you may have to solve the problem along with here now approximation, so that you may shrink it out of some here principal components. Then you may use such pseudo inverse so that you can get here now, let's say that is xk, that can be here now V and sigma K plus and U transpose and P. Then that is along with the truncated metric, and so that is a sort of pseudo inverse of AK, and you can get some solution. And sometimes this solution is way better than here the X. So you can use it for at least for solving a least squares problem. Okay. Here the corollary is now here assume A has full rank, and that means rank of A is n. Now, okay, sigma 1 to sigma n are singular values, and sigma n is the largest positive singular value. And B is a metric such that the distance from A in L2 norm is less than sigma n, then also B has a full rank. That's the corollary. That means that here, earlier when we introduced singular value decomposition, basically we try to get the maximize the variance, and so that the singular value is a sort of a magnitude of the eigenvectors, eigencomponents, so that here singular value is a sort of a power or magnitude of those components, so that now the power is only different, only small amount, then yet if you consider singular value decomposition of B, then yet, and that's the largest, the singular value must be positive. Okay, the smallest singular value of B must be positive. That's the idea behind this corollary. So you can prove rigorously, but roughly you can think that way. Okay. Okay, here, right now, we consider shape of SVD in this way. The original metric is a tall metric, then U has this shape, and now and sigma and V transpose are here the square matrices. But you may try to get here full singular value decomposition. So here U is now the square metric, so it's a huge metric, and here V is also square metric. To match dimension, here sigma is now becomes tall metric. In this way, you can compute it. If you are using, for example, MathTalent, then the default shape of output is given in this way. And so that this portion, okay, from here, that is a sort of extra part from here, okay, and from here to there, some extra column of U is made. This is by using random generation, it is made. So it'll be attached. But if you are using some key, I believe that is econ. When you are using SVD in MATLAB with the option and econ, then the output will be changed into this form. And however, in practice, this portion is useless. And so that getting the output in this form is okay. Okay? Okay, this is the end of the second part. Thank you.